Good morning, everyone. Welcome to the webinar series of Future of Computational Chemistry held by Department of Chemistry Education, Indonesia University of Education, or Universitas Pendidikan Indonesia, in short, UPI, in collaboration with Indonesian Chemical Society, Himpunan Kimia Indonesia, or HKI, Jabar, Banten. I am Mita Nurhayati from Department of Chemistry Education, Universitas Pendidikan Indonesia, will be your moderator for today's seminar. First of all, I would like to say thank you very much and gratitude to our invited speaker, Professor Superhua and Dr. Muhammad that has joined with us this morning. I do believe that your expertise, especially in computational chemistry, will add great value to the evidence on this seminar. Yeah, we have our students here and also other participants from outside UPI and also lecturer from Universitas Pendidikan Indonesia as well as other university. And I also would like to say thank you very much and give appreciations for all of the participants that joining with us on this webinar. I really hope to see you all in person here in Bandung, but yeah, unfortunately the condition is still not let us. So I wish you the best health during these situations. And this webinar follows the visiting professor series in computational chemistry that held by Department of Chemistry Education. For your information, we have 7 lectures presented by Professor Supahanungbua previously in our computational chemistry course. And if you want to follow the lecture and the course from the beginning, you can visit us on our YouTube channel and find the playlist of computational chemistry course. Yeah, it is very insightful and you can learn about fundamental of computational chemistry as well as applications to solve the real world chemistry related problems. And this seminar consists of 2 sessions of talk. Each lecture will take 45 minutes, followed by discussion sessions after all presentations. And if you have any questions regarding the presentations, or if you want to get some suggestions or advice regarding your research maybe from our speakers, please kindly write that, don't be hesitate on the chat box. And you can also deliver your question directly to our beloved speaker here by clicking raise hand. Then you can talk after we let you open the microphone, if you're still hungry. And I would like to inform also this activity in Zoom meeting is recorded and live streamed in our YouTube channel. So you can also invite your friends or your colleague to join our meeting today. Or maybe if you want to rewatch the recorded version, you can go to our YouTube channel. And yeah, talking about computational chemistry, it is one of branch of chemistry that employ computer to conduct calculations in order to predict or explain chemical phenomena. Yeah, therefore, computational chemistry should be connected with experimental chemistry, of course, even we work in the in our computer. And very fortunate that today our first speakers here, Professor Supahanungbua will present about how are the trends in computational chemistry research in the future and or related to quantum computing or sustainable development goals and the opportunities of computational chemistry to strengthen the basic research in our country, in Thailand and Indonesia, and also opportunities for young scientists career in computational chemistry in the future. So I would like to introduce a brief introduction of Professor Supahanungbua. Here we have Professor Supahanungbua. Pak Hafiz, can we move to other slides? All right, Professor Supahanungbua is come from Department of Chemistry, Faculty of Science, Kasetsart University, Thailand. Yeah, hopefully we can visit your university.
Yes,
maybe
sure.
someday. Yeah, and she is also the president of the Chemical Society of Thailand, or CST. So the person in front of us is the most important person in Chemical Society of Thailand. And yeah, it is very great and valuable and precious moment for us. And this is some research interest of Professor Supa, of course, in computational chemistry and computer-aided molecular modeling and drug design, QSAR, 3D QSAR, protein-based drug design, bioinformatics, cheminformatics, data science, nanopolymer, conducting polymer, and green chemistry. Hopefully, if you have the related research interest with Prof. Supa, we can have a fruitful discussions after this meeting. And this is the educational background. Okay. And she pursued her bachelor degree in Chulalongkorn University, as well as her master degree in the same university, and the doctoral degree in University of Innsbruck, Austria. And this is some honors or awards or recognitions that she had received. She has been the highest age index awards in physical science in association of 55th anniversary of Faculty of Science, Kasetsart University. And as we know, she is the president of the Chemical Society of Thailand and board member of the Asia Pacific Conference on Theoretical and Computational Chemistry and IUPAC Standing Committee on Publications and Cheminformatics Data Standards. This is two recent publications, I guess, for more than 100 publications that she had written, and yeah, you can further find out more on her Scopus profile or Google Scholar. So without any further ado, Professor Supa, time is yours.
Okay. Thank you very much, Mita, for your kind introduction, and Professor Muhammad, and all distinguished lecturers and audience, students, ladies and gentlemen. It is my great pleasure to be here to share my research experience for the lecture on computational chemistry. And I'm very happy to meet Professor Muhammad, who is my old friend. Actually, we know each other for many years.
Yeah.
Nice to see you. Yes. And so I like to share my slide. Hope that you can see already present. Okay. Yes. And we shall talk about the future, because our future based on the young people, young chemists, young scientists. Okay. So as Mita has already introduced, some points may be discussed about the trend in computational research. And also, actually, I will not talk about much about the quantum computing, because it's very early stage, but we can think about it. I mean, prepare today for future, and also very close to the SDG, okay? And probably we can see how we can strengthen our opportunities in computational chemistry research to strengthen the basic research in our country, both in Thailand or Indonesia. We can discuss. And for sure, I really concerned about the young people, because you are our future. And then I will talk by sharing from my research experiences since I was a young chemist almost 30 years ago. And then I think when I look back, I have seen something. Okay. So for quantum chemistry or computational chemistry, this field of research has been actually almost 100 years if we look back. And from time to time, as I talk in the lecture, that those great scientists have done their very excellent job in fundamental, in mathematics, in physics, in chemistry, and also in biology. And these provide the challenges for us to apply the computational chemistry to explain the real world problems. This is the key concept of computational chemistry. we need to model the real system, okay, and based on our available methods, which already developed from time to time, however, still needs a lot of put and effort to develop the method. And the computer simulations technologies and also development in data science provide this computational method to be developed to be the good model to explain about the experimental data, and then we can predict whatever we would like to have, both in biological science and material science. So if we look from the database of the publications, if you use computational calculations keyword, then you can see something very exciting that just only 10 years, this publication has been highly published and up to 70,000 publications a year. And here, just September that I collect this data, but you can predict that it will be exponential increasing. And also the countries that done a lot of work in computational calculations based on the United States, okay, in the orange, but just only a few years, you can see that China has done a great job on that. Okay, so for us, I mean, in ASEAN, in Thailand and Indonesia, we are how to say, we are increasing in number of publications. I mean, in number of basic research. That is good. So if we look for the SDG or Sustainable Development Goal, chemistry is the central of science. So molecular economy is that we can learn a lot of molecules to be some kind of drugs or bioactive compounds to fulfill our needs in medical science, and also for food technology, textile industry, cosmetics, information technology, or energy. So these are the things that chemists shall be able to understand about the molecules, the structure of the molecules, and how to use those structures to be impact on our needs. Okay, this is the way of the SDG. So next year would be the International Year of Basic Science for Sustainable Development. So we need basic science to solve our pain point and our real world problems. This is a concept. And if we look for the supercomputer in 2019, you can see that China was the best at that time. But right now, you can see that just already this year, about September, that we searched this information, you can see that there are many of the supercomputer available in Japan, in United States, or in China. And these also very active area. And you can predict in about 5 or 10 years next, we will meet the progression on quantum computing, yeah, and it would be something that change our life again, okay, but those are the future. So we have to prepare our people today for that, okay. So I like to sharing some research experience. It's important that we have learned something from our senior or our tough professor in the past. And my research experience in Department of Chemistry at Kasetsart University would be focusing on molecular design. And I would like to share you about how to model the drug, okay? So we have the platform of bio and chem informatics, which quantum chemistry, computational chemistry will be there. And also for the application of simulations, we have MD simulations, we have docking, and then we work together with the organic chemists who screen some natural products and also modify of the organic compounds or bioactive compounds. And then we can use quantitative structure activity relationships to design the molecules. On another hand, we have also collaborated with the molecular biologists who prepare the structure of the enzyme and do also the complex between the enzyme and the inhibitors. Not only the X-ray crystallographic study, but also protein NMR, which represent the complex in the solution. Okay, and also I have used the same technique, molecular design, that we can be able to design some materials. For example, some conducting polymers or the fluorescent compounds that can show the difference in the fluorescence and the colors, okay, that we can simulate in the computer and predict what happened in the chemical reaction or the kinetics. And this also very active. And recently, I also did some advanced optical materials, okay? So you can see that we have some kind of the young people, we need to look in the, how to say, the whole picture of the process, not only just the work that we done right now. For example, we do the thesis, we do the graduates research, or we do some postdoc research. It is a one piece of work, okay? But we need to have the scene, yeah, the long-term research that from the starting, from the very beginning of the fundamentals, probably you can think about some kind of target discovery, hit generations, lead optimizations, and also if we pass this, we can apply our proposed lead compounds to the animal models, and later on will be the work of the drug development. So we are drug discovery, okay? And the information that available right now is the bioinformatics for target identifications and the cheminformatics for molecular design. And if we focus on the chemical information for drug discovery, we have some kind of core knowledge over here. This is the core knowledge and also the core technology. For example, we have the structure-based drug design that including molecular docking, virtual screening, homology modeling, and molecular dynamic simulations. And also we have the ligand-based drug design, including the QSA pharmacophore modeling, including the virtual screening and molecular database. And also we need some kind of computer prediction for predict the pharmacokinetics prediction, which very helpful for further drug development. So if we can pass this, we can think about the successful drug discovery or drug development later on, okay? And one of the core knowledge that we have discussed, that means computational calculations, and we can apply quantum mechanics and molecular mechanics to study the enzymatic reaction. And at present, we have the machine learning, you know that, and it is very exciting research that we can use the core knowledge and technology to serve the machine learning research in very near future, okay? So the core knowledge and technology that I mentioned, we can use it to apply for different molecular targets. For example, at QSA University, we focus on different molecular targets, especially for the problem for the national needs, for the global needs, okay? And one of the very highlights today that I would like to sharing with you is the antivirus, especially for the anti-AIDS, which actually molecular target for anti-AIDS drug discovery would be the target like HIV-1 reverse transcriptase, protease, integrase, and recently we also apply to the feline immunodeficiency virus. That means the structure are quite similar. So we think about drug for animal as well, okay, like FIV-RT or FIV protease. Not only AIDS drug, but also dengue, which is the main problem in our Southeast Asia. we study on the NH3 protease or SARS coronavirus. If you remember, it was outbreak some times ago, about 10 years ago, that's SARS first outbreak. And we apply our national product database to screen for the SARS coronavirus protease inhibitors. If I have time in the second part, I may show to you about the results. And for sure, avian influenza, okay? And at present, we also focus on COVID-19, and we like to see the interaction between the antigen and the spike protein of the COVID-19. If I have more update information, probably I can share with you in the future. For the target that probably we can see the common interest between Thailand and Indonesia, probably can be anti-malarials, TB, cancer, Alzheimer's disease, inflammation, and also antimicrobial resistance. So you can see that with the core knowledge and technology, we can apply to anything that we are interested in, okay? So let's look. In 1995, when I graduated and then I tried to start my initial independent research, I just searched to the literature and found that anti-AIDS is very important at that time. So I start to work on HIV-1 reverse transcriptase inhibitor, especially for the mutant enzyme. And very luckily, in the year 2008, two scientists obtained the Nobel Prize in Physiology and Medicine due to their discovery of the HIV, human immunodeficiency virus. So make us very exciting that we work on the viral infection, and there are several targets. For example, HIV-1 reverse transcriptase, protease, integrase, or even the membrane or spike protein or what else. But for us, we try to focus on HIV-1 reverse transcriptase enzyme. Just focus, just to learn from this target. And we can try many of challenging, okay? And at that time, there was only the first generation drug like nevirapine, and later on, there are some second generation developed, and up to now, we have the third generation HIV-1 reverse transcriptase inhibitors. And it is important to focus on non-nucleoside reverse transcriptase inhibitor because it's very specific to the reverse transcriptase and low toxicity. However, the problem of virus, it always mutate, and the key mutation are these: tyrosine 181C and lysine 101 to asparagine. So our work apply the computer-aided molecular design that try to see the fit of the structure and the enzyme. This is the concept of the lock and key. Probably most of you familiar with this, and you can see that the drug target can be enzyme inhibitor, receptor and agonist, antagonist, ion channels and blockers, transporter, even the DNA blockers. So there are so many things that we can learn from that. And as I said, we have a receptor-based drug design and ligand-based drug design. And we can see that the pathway of drug discovery can start from how to get the genome, or how to modify, or how to mutate the enzyme, and then we can apply some biological assay development. My colleague also developed the assay for HIV-1 reverse transcriptase, and also we modify the structure from our design, okay, and test for biological activity. And at the end, we need the ADMET prediction. These are the way that we have done for multidisciplinary research. We cannot work only ourselves, okay? We need the collaborations. And after some time that I work on this for about 10 years, producing some publication and make our team, also myself, learn a lot that for computer calculations and molecular modeling can provide the fundamental information. For example, we can understand about the conformation of the inhibitor upon binding, drug enzyme interactions, and flexibility of the enzyme, protein-based drug design, virtual screening, and the enzymatic reaction, and many more from HIV-1 reverse transcriptase. And here is the example that we study on the conformation of 3 inhibitors. But upon binding, these different structure change their geometry, okay, their conformation to be some kind of a so-called butterfly-like shape. You can see that left ring and right ring of the butterfly upon binding. Very nice. And later on, we apply the QSAR, quantitative structure activity relationships, that even is quite classic for about 50 years already. But I would like to say that the concept is very important because we can generate the descriptor of the molecules based on the molecular descriptors in order to relate with the biological activity. This is the concept. That means if you know the structure, you know the activity, you can propose the mathematical modeling. Okay, this is very, very easy concept. The left-hand side is the activity, biological activity, and the right-hand side are the set of physical chemical properties, and be represented by molecular structure. And the limitation of QSAR is that it needs to work on the analog of the of the molecules. But whenever you have the biological activities, you can construct the descriptors and you can propose the mathematical model in order to predict for some kind of the unknown or the new molecules. Okay, this is the way that QSAR can help the medicinal chemistry to design and then to go to the bench to synthesize the compound and save the time, save chemicals, and kind of successful research. So the principle of QSAR quite important because as a chemist, we know about the structure of the chemicals, and then we go to the bench and work on the experimental measures on biological activities. And this way we can work on the drug design research. On the other hand, if we have the structure, we have the experimental measures for physical chemical properties, we can do a lot of materials design, okay? And during my lectures, I also I also demonstrate some of my material design, optical material design to the audience, to the student. So I just like to mention that if you are interested in, QSAR is one of the good method that we should learn for basic, okay? And then we can apply molecular descriptor both to material designs or drug design. And very active research right now is the artificial intelligence and machine learning. And they use this concept, okay? Structure, property, relationships. Very exciting to see this kind of work. And I would like to say that at the about 1995, the comparative molecular field analysis or 3D QSAR has been very, very famous and popular. And so we apply to HIV-1 reverse transcriptase for HEPT analog, nevirapine, and TIBO analog. And then at the end, we design some candidates. And we combine with the molecular docking, which try to rank the binding of the series of compounds based on the function, okay, the free energy of function. And these are quite popular up to now, and not only docking, but also molecular dynamic simulation. And then provide us opportunity to learn about the chemical reaction mechanism or stereochemistry or molecular shape complementary of the receptor, and also the electrostatic fields that we can explain about the electronic properties of the receptor, or even some kind of weak interactions that we can help experimental chemists to explain what happened in the binding site. And here is the quite good example that this green structure is the nevirapine, the drug, the real drug. And we compare with the design compound 668NV that we model the side chain of the core molecules. And you can see that from docking and MD simulations, we propose that this new compound is better binding than the drug itself and very helpful. And also it can screen the series of compounds. You can see that we have about 23 compounds and screen out those less inhibition or less binding. And then we can focus on the good candidates. Also for molecular dynamic simulations, it shows us about the flexibility of the molecules upon binding. And we can also focus on the number of water molecules that stay in the binding site. It's very interesting. You can see this molecule, water molecule. When we do further work, we propose that upon binding, the drug binding, it needs one molecule, water molecule, to be bridged between the inhibitor and the histidine 2, 3, 5. Okay, so this very interesting work, I would say. And the technique that we apply for this work is the MMPBSA that thermodynamics itself can help to explain what happened. And one of the things that I like to say that quantum chemistry is very useful to see the drug inhibitor interactions, even for the weak interaction. If some of the students remember that I mentioned about the ab initio cannot include the dispersion interaction, okay, or the correlation interactions, but we need the MP2, okay, or the density functional theory to help. And Professor Keiji Morokuma proposed a very good idea, the onion idea. That means we can separate the system to be 3 layers. The inner layer can apply by a very high level of theory like MP2 or B3-lib. And the second layer, intermediate layer, and the lower layer, the outer layer, can be applied by Hartree-Fock or semi-empirical. Okay, so this way provide our ability to understand about drug interaction, and these are the extrapolation of binding energy. Very clever. And Professor Keiji Morokuma once tell me that he got this idea when he fly over from the US to Japan. Okay, his hometown is in Japan. Okay, and then when he stay in the airport, just transit, and then he think about how to solve the very complication problem. And the onion, you know, the onion that we can have many layer, okay? And then he said, okay, this very good idea. Then he applied onion to his extrapolation energy. So he used our own N layer molecular mechanics, okay, and so on, that represent the onion, okay, by using the onion itself. Very nice. And later on, we apply this to HIV-1 reverse transcriptase. And here is my mentor, two of my mentors, Professor Keiji Morokuma. He actually was the PhD graduate of Professor Fukui. If you remember, Professor Fukui was the Nobel laureate in chemistry, and he is the first Japanese who won the Nobel Prize. And Professor Keiji was his key PhD student at that time. And he is a very great chemist, I mean, theoretical chemist. And it's a pity that he was passed away some years ago. Anyway, I really respect him. And the second mentor, Professor Peter Walshan, who is the professor in theoretical chemistry from University of Vienna. He has my long-term collaborators, and I really also respect him for his support, not only me, but also my graduate student. This is Dr. Vicha, Dr. Ponpan, who is the head of chemistry department in Ubon Ratchathani University, and all of these are my PhD graduates. I'm really proud of them, and also my collaborator, Professor Keiji Mori, and some Japanese professor who collaborate with us. Okay, so here are the example of onion calculations that we can explain how the dispersion interaction, pi-pi interaction between the drug and the residue in the binding site. You know, this cannot be done without the MP2 applications, and we cannot do it because the structure of the enzyme very huge. Okay, almost many hundred of the amino acid. Okay, so this is very nice work, really. And not only that, we also try to do the virtual screening from library of the compounds and end up with the small candidates. And we try to also generate some of the nevirapine series, okay, based on pharmacophore modeling, and screen of this candidate. At the end, we propose two compounds, NPTN14 and NPTN15. So please remember these two structures. I will talk about it later. These are from our modeling, okay? And at the end, from the library of the compound, we end up with the good candidate and go to the bench and try to test how about its biological activities. Another approach, I think I have some time left. So mechanistic investigation of the HIV-1 reverse transcriptase, also very nice work that we can focus on the catalytic site and model with the primer and DTTP to magnetic to magnesium and aspartate for the quantum mechanics treatment, and the rest of the simulation we apply by molecular mechanics. Okay, so here are the results that we obtained. You can see that when catalytic triad happen, okay, the oxygen of this aspartate 185 will abstract the hydrogen of the the primer. I'm sorry, the primer, and then the cleavage of the pyrophosphate happen. So from the simulation, you can see the oxygen of the aspartate abstract the hydrogen of the primer terminus, and then resulting in this oxygen will be attached to the phosphate of the substrate. Okay, so we can see some nice cartoons from the simulation. This is quite tough. We use the charm, and charm also apply the QMMM simulation on that. Okay, very tough work. Another enzymatic reaction has been working on the cis muconate lactonizing enzymes, and we apply the DFT QMMM study. Also quite interesting, and we can explain what happened and energy profile of the intermediate, and then we can propose about the enzymatic reaction. And also recently we apply this to the, this is quite tough work also. It is the catalytic reaction of plant allene oxide synthase via quantum mechanics and QMMM calculations. Okay, and everything that we have done, we produce a PhD graduates. And this kind of research is that the output is not only the publication, but the high potential master degree graduates or PhD graduates, and then they are very smart on their career. So I like to give some example, as I mentioned in the beginning, that computational calculations have to work with the experimental scientists. And this one is that we collaborate. This is my PhD graduate, Dr. Vicha Trisuwan. We collaborate with the Professor Simon Mackay of the Satkla University, and we interested in the DNA minor growth binder, okay? And for the experiment, we apply the isothermal titration calorimetry to provide the binding energy that we obtain about -10 kcal per mole. And on the other hand, we also simulate MD simulation. And the question is that, can we predict the binding energy based on the simulations? If we can do that, that means we can design the DNA binding minor growth, okay? Then we can design the new structure, and then we can do the simulations, and then we can see if it can block the DNA or not. This is the idea. And based on the MD simulations, we have many protocols, I would like to say, not easy at all. We need to design the DNA and non-polarized, DNA and polarized, and you can see that quantum chemical calculation can be helpful to apply to the ligand. You see that we have the B3-lip and Hartree-Fock, okay? And at the end, we obtain the very good prediction based on the model MD3 and MD4 that we can predict exactly to the experimental, okay? And this kind of simulations can help the scientists who try to synthesize the ligand DNA complex, okay? And this work has been published in Physical Chem and Chemical Physics and put in the cover front. Really nice to see. You can see that here is the structure and the molecular mechanics, and also the NMR and some experimental work that work together. So now I like to give you a little bit more. If we can design and then we can synthesize the compound to be HIV-1 reverse transcriptase, if it's possible to do some kind of further work. And recently, not recently, actually quite some time, 5 or 10 years, that we try to work on NMR analysis of the new design inhibitors. It's really tough work, I would say, really tough work, not easy. But we succeed. Finally, we success. I have 3 PhD students who work from time to time, okay? And finally, we can work on NMR of this drug, nevirapine, efavirenz, and rilpivirine, and also this synthesized Na14 and 15, okay? These are the design, and then we synthesize. And finally, we found a very common series of nevirapine and the new synthesized that they start, they provide a similar binding. And there are the movement of methionine that we label methionine, and we can see the movement upon binding. This is the apo form without inhibitor, and this is with inhibitor. So you can see the movement. That means whenever the inhibitor bind to the binding site, we can detect the movement of methionine 2,3,0, okay? And also some pattern happen with the efavirenz, 2nd generation drug, and the 3rd generation drug, rilpivirine. But very exciting when we compare the carbon-13 chemical ship of those compounds with the PEC50 that we obtained from some publications. And we try to correlate, and you can see very nice correlation between the low inhibition to the better inhibition. And it's really discriminate the 1st generation, the 2nd generation, and the 3rd generation drug, okay? So very exciting results. Recently, we also try to find other opportunities for HIV-1 reverse transcriptase, and it was inspired by this work. In 2011, aptamer can be also inhibitor for HIV-1 RT. So we start to study on the aptamers, try to find the DNA library and screen for the good inhibitor, okay? So very exciting by the MD simulations, and it proved that the aptamer can bind and can stop the DNA replications, okay? And I have not much time, but just to give you some idea that we have the MD simulation, and then we go to the bench and work. My collaborator, Professor Getavi, and also my PhD student and collaborator, Professor Koichi Kato from Institute of Molecular Science, Japan, that provide our opportunity to work with the NMR, this machine, very tough work on that. However, we can propose some aptamers, okay, to be better than alpha variants. You can see that the aptamer is better, yeah, wild type and mutant type percent inhibition is better by the aptamer. And at the end, we apply NMR simulations, NMR experiment, and end up that we have the two proposed aptamer RT1T49 and KY44. So this is very nice. I mean, very recently, we just published this kind of work this year. And when we look further, okay, we have so many experience, and then we apply to the furin immunodeficiency virus, the cat, okay, the cat, our animal, there is no drug for them. They have to use the same drug as human, that so expensive. So we try to study and to understand. And for the HIV1-RT and the FIV-RT, actually the structure are very similar. You can see that 48 identity and 67% similarity. So very nice work on that. And we screen some candidate from mushroom. Especially we construct the database of 50 eatable mushroom, and we found about 600 compounds of this library, mushroom library, and search for candidate for FIV1-RT. And now we have some progression on that. We have some candidates from the eatable mushroom database, and then we can do many simulation on that. Okay, so I shall have some good result to update you in very near future. Yeah. Just to come to the last part of my talk, I showed to you about just one example on antivirus AIDS, okay, HIV1 reverse transcript test, and a little bit further to the furin, but actually we have many more. So if you are interested in any kind of target, we can talk to you later in more details, but just give you a little bit how to say, I'm very inspired by Indonesia, because you have so many biodiversity and lots of good natural products. So we can do a lot, and based on innovative extraction that we are trying to put the green process and combine with the innovative computer technologies that I just showed to you about computer-aided molecular design, quantum chemical calculations, and computational calculations. At the end, these have to be collaborate with the omics technology to try to have something happen and good for our well-being. Okay, so I think we have inspired by many research work and opportunities for computational chemistry to be impact to solve the real world problems. There are so many things. Okay, and we try to find a good well-being of the people in our country, in our nation, in our globe. Okay, that the basic research is important if we like to solve the pain point 17 issues of the SDG would be happen. And for the young scientists, and you have to think about your career development. If you are interested in chemistry, computational chemistry, that are good challenging for you and many good opportunities. Yesterday, my colleague from medical research just called me, Ajahn Supha, if you have graduates in docking, graduate student who can perform docking, he need one. Okay, so I have already 1 and 2 PhD candidates. So I introduced them to the medical doctor, so they get a job. Okay, very good. So just try to find project that give you pressures and enjoy the research and create new idea by sharing with other scientists, other senior and conferences, and raise some sharp question. Especially think a little bit more deeper in what you have done right now and for future. So thank you very much. I need to thank my grants and my students, my colleagues, and many of collaborators who helped me to work on this. And thank you very much for your kind attention. I think I finished 45 minutes. Thank you.
Okay, right. Thank you very much, Professor Supa, for the great explanations about computational chemistry research, current computational chemistry research. And we always, how can I say? We always inspired by the experimentalists, of course.
Yes.
Right. And okay, we can move to other discussions because I guess some experimentalists thinks that computational chemistry is an exclusive branch of chemistry because we need some computers to conduct the research. But now our second speaker here, Bapak Dr. Muhammad Abdul Qadir Marto Prawiro, will introduce you about how to build and develop computational science community in Indonesia with new tools to access frontier methods in computational chemistry and computational science in general, and the roles of computational chemistry in collaboration with experimentalists to accelerate research and discovery in strong points of Indonesia, such as natural product chemistry, elements from Earth, including rare earth metals, and also thermophilic enzymes from Ring of Fires. And third, it is about opportunities for Thailand and Indonesia to develop combined database on natural products and the quantum mechanical studies on their molecular resources, example on QM sites using QCLDB2. Yeah, it is very interesting topics we have today. So, Pak Kakak.
Okay.
Before we start our talk, I would like to introduce first about a brief introductions of Pak Kakak, but I believe that almost all of the participants here already know you because Dr. Muhammad Abdul Qadir Marto Prawiro is the lecturer from Department of Chemistry, Faculty of Mathematics and Natural Sciences, Bandung Institute of Technology, or ITB. And right now also you become a head of study program in ITERA, Institute Technology Sumatera. And he is also the chairman of Indonesian Computing Society. And the research interests, including physical chemistry, theoretical chemistry, and computational science. And he pursued his bachelor degree in Bandung Institute of Technology, as well as his master degree. And he also continued his doctoral study in the University of Sydney, Australia. And can we move to the next slides? Pak Hafiz, can we move to the next slides? Okay, and this is some recent honors, awards, or recognition received. He is the former president of Indonesian Chemical Society, or HKI, in Indonesia, such as Prof Supa, and he is a chairman of Indonesian Computing Society and the current coordinator of chemistry study program at Sumatra Institute of Technology, or ITERA. It is some of new publications of Bapak Dr. Muhammad Abdul Qadir Marto Prawiro. And if you want to know further about the publications, you can go directly into his Google Scholar profiles or Scopus. Okay, without any further ado, Pak Kakak, if you are ready for the presentations.
Okay, thank you for nice introduction. Good morning, Professor Supa, Bumita. Okay, yeah, nice to meet you. Okay.
Thank you.
I would like Professor Supa has present a nice presentation about her research and also about the computational chemistry. I would like to share on other sides of that, especially in the organization and community development. Okay, wait a minute. I will share the presentation. Share screen, and then yes, this one. Okay, can you see the screen, the slides?
Yes, doctor, it is very excellent.
Yeah, okay. Yeah, the future of computational chemistry, with the subtitle, actually it's roles and community development. Okay, just summarize what Professor Supa state, that computational science in general, at the beginning, it's only a bridge between theoretical and experimental science. So the new methods in theory, the new theory with new, for example, differential equations and etc., should be tested by the experimental data. So computational science have a role as a bridge, and they translate the theory into algorithms and then try to obtain numbers from the calculations and then compare with experiments. But in the development of computational science, it's not only a bridge, but as a methodology for new discovery. For example, new discovery of materials before it is synthesized or produced. So it becomes a new field in science. Okay, it's also experimental chemistry. So this page. The future of computational chemistry, core skills are evolving, understanding the basic of chemistry, for example, new methodologies, great visualization, new algorithm for quantum chemistry method, etc. And also the natural development from computational chemistry or from computational science is, I explained this a bit. So in the beginning, there is like Galileo Galilei, it's observational science, or taxonomy of plants without any manipulation of the nature. That's observational science. And then the natural development from observational science is experimental science. And then next, we would like to explain why the data is like that. So the theoretical science was developed with advanced mathematics. And then the theory becomes more complicated over time. So we need to translate the theory into algorithms so we can use the equations to produce some prediction or some numbers from calculation, and so we can compare with observational or experimental data. But the next natural development from computational science is that we face big development in the numbers of data. So we have to make it understandable, or we have to produce insights from the data from computational calculation, or the data from very complicated and advanced instruments through experiments. So the natural development is data science. So in the field of chemistry, I predict that the next development from experimental, theoretical, and computational, there will be data chemistry. The data chemistry is comprises of like bioinformatics, cheminformatics, chemometrics, and etc. And new subfields of science. So there is our future, I think. If we try to search data chemistry right now, there is no such term, but probably in the future we will find data chemistry as the development of data science evolving. So this is some development, for example, because the theory and also the methodology and then the syntax of many software in computational chemistry, some researchers face the needs to develop some tools to access many like computational tools, some interface. So one of the interface is atomic simulation environment. This is, for example, there is a big development in Orca, for example. This is Orca with the new version in July 2021. And then in US, NWEC, there is a project right now to develop NWChem into NWChem X. They said NWChem X, with a new development with theories, methodology, and also algorithm and hardware, exascale computational computers and networks. So we will find many interesting development in computational chemistry. So in Indonesia, we check this atomic simulation environment and then test the capability and also the features, and would like to use it as our tools in online workshop series, for example. We found that the development is not cannot not too fast as the quick development of the theory in these softwares. So, for example, they can access the basic calculation in Orca and many softwares, but cannot access some of the new features. So in Indonesia, we develop computational, molecular, and material design environment to access the new features, and then make some workshops to introduce the tools to the researchers and also students. What the aims of the activities is to build and develop critical mass in computational chemistry researchers and also students that are interested in this field. For example, we use the Ministry of Education program Merdeka Belajar Kampus Merdeka and develop a package, course package in computational chemistry. Currently, we develop, for example, a package for the minor of for other disciplines also in the fields of computational chemistry with lectures like computational molecular and material design, and then basic and advanced molecular dynamics simulation, and etc. And it will be developed by different universities. For example, for CMMD, Computational Molecular and Material Design, and then introduce CMMDE, Computational Molecular and Material Design environment. The university involved is Institut Teknologi Sumatera and University of Pertamina. But for the simulation, molecular simulation, molecular dynamic simulation, ITB will develop. And then for basic computational chemistry to understand basic concept and principles in chemistry, University of Gajah Mada will develop the course. And then next year, we will launch the lecture package on computational chemistry. So, yeah, we also have a meeting last month with Indonesia Mining and Mineral Research Institute, the R&D unit in holding company of mining industry Indonesia. So we propose to develop collaboration to develop research streams on tin, for example, or nickel, not only for construction materials, for example, but also for material like catalysts and etc., molecular device in the future, etc. And for organic chemistry, we would like also to collaborate with Society of Indonesian Natural Product Chemistry. This is some development, some examples of development. This is, for example, this is what year is it? Let's see in the Google Scholar, for example. Case study is 2020, October last year. It's about EPR, the new the new journey into EPR to predict EPR hyperfine coupling constants. It's very, very advanced calculation because it needs accurate calculation and also use ab initio molecular dynamics. This is a very hungry calculation, actually needs high performance computing power. This is another example. The computational chemistry community also always research on also to choose new basis sets and also compare many basis sets that is developed by many institutions. So, and also always developing the old methods, but with new theory that is adapted to possibility to increase the speed of computation. For example, this one. And also, for example, develop database to do benchmarking of the computational chemistry calculation for thermochemistry, kinetics, and also for supramolecular chemistry, non-covalent interaction. That's some of the examples of new developments that we should, the community in Indonesia should also follow the development. This is one of the collaborations that will develop the MBKM course packages is a consortium on computational science development. The institutions involved are BRIN, also IPB, ITB, this is ITS, Institute of Technology in Surabaya, Institute of Technology 10 November, Institute of Teknologi Sumatera, Indonesian Computational Society, this is Gajah Mada University, Indonesian University, and University of Indonesia, and also University of Pertamina. So it's just signed in this month, and our program is to develop packages, lecture packages on computational chemistry under the consortium. So our target is in the academic year of 2020 and 2023. We have tried this out in 2 years, CMMD 2020 for researchers and CMMD 2021 this year is currently running. It's for students. So next year, we add the courses that I mentioned before. ITB, for example, develop molecular dynamics simulation courses, and UGM develop the basic computational chemistry to understand basic concepts, and not basic computational chemistry to understand basic concepts and principles in chemistry. So it will be dual activities. Dual activities means that the course will be included in the package of computational chemistry for students in various universities in Indonesia, but can also be developed for high school chemistry teachers. So the workshop can titled, for example, computational chemistry workshop for high school chemistry teachers, because this is about how computational chemistry used to understand basic concept and principles in chemistry. So that's the plan. And then this is last year activities, computational molecular and material design to 2020, using, for example, the new method in DC-DFTB MD from Waseda University, and also XTB from Germany, Bremen, I think, and also DFTB plus, the new theory and methodology in computational chemistry. This is the FTB plus, and etc. And then also introduce how to design electrolyte for battery, for example. So we use DC-DFTB MD in this activity, in this workshop, and also how to model proton diffusion and other diffusion in solution, and also computational organic chemistry to find like transition states. So we can choose which routes or which mechanism that good for new synthesis, or for green chemistry to find new routes to synthesize some chemicals that more friendly, more safer, and etc. Computational, and also biomolecular circuit preparation. This is for biomolecular biomolecules using also DC DFTB, XTB, and DFTB plus, and also DOC6 for docking, etc. And also for solid state. So we would like to develop many different communities in computational chemistry. Some will focus on solid state, for example. Some will focus on biomolecules. Some other will focus on organic reaction mechanisms, and others in computational nanoscience. In this year workshops, for example, we add topics in computational nanoscience to design, for example, nanocatalysts and etc. So this is the idea. The idea is that this is in 2020 first. We in 2020 the program is for researchers, and then in this year we open that for like what's it? We call it elective courses for students. Elective courses for students from many universities. The participants is about 20 students probably, and then 30 researchers this year. And then next year we will start the package for CCSD computational consortium on computational science development for long-term program. So not only one courses, but also many. This is MK means courses, mata kuliah. That's our plan for next year. And also, this is the closing. So we need critical mass to accelerate growth and applications of computational chemistry in Indonesia. Some factors is strengthen collaboration, clarify the roles of computational chemistry and computational chemists in Indonesia by developing many sub application of computational chemistry, and we hope that it will increase funding opportunities for this field. The next natural development of computational science is data science, so that there will be data chemistry that comprises chem informatics, bioinformatics, chem inverse, and other terms, other new terms in the future that we don't know yet. To support the development, we need databases on computational quantum chemistry research, including database on compounds from nature studied by computational chemists. So probably we can develop like combined database. There will be a database about the natural product, the isolation, for example, the synthesis to the reaction to become another compound with added values, and also the characterization, and integrated with the database of the study by computational methods. So I think it will be interesting to combine those both community, natural product chemistry and computational chemistry community to accelerate the growth of the two fields in Indonesia and also probably in Thailand. Okay, and I will share some of the tools. For example, wait a minute, I will share the screen. This is our server for computational chemistry online workshop series. We develop actually the person that mostly developed this script is Pak Aditya Wibawa Sakti from University of Pertamina. I give him some ideas in the beginning, what will be developed. So we have CMMDE script and CMMDE pre script. This is pre means before main calculation. For example, to change from one format to another format, for example, for a molecular representation, from smiles to XYZ, Cartesian coordinates, for example, and other tools. For example, also to add hydrogens to biomolecules from X-ray diffractions. So add hydrogens for checking the completeness of amino acids in the polypeptides, for example. That's CMMDE pre. And CMMDE PY is for main calculations. For example, we can choose the software Orca or NWChem. So we can compare both. And we don't have to be confused with the syntax because the syntax will be the same. The input, we need only input of geometry of molecules. So the input for charge can be like this, and the input of geometry will be like molecule XYZ. And then this is the charge is -1. If we don't write this optional comment, the charge assumed to be 0. And then the job is, for example, optimization or optimization with frequency calculation, and etc. We can use also, for example, this is WinS doc using doc6, and this is what kind of calculation we do here. This is the input, and etc. And for the CMMDE post, the last one is CMMD post script. This is this script is to to process the data from calculation. For example, we can process data from Orca or NWChem. So they will read the output and then inform the user, for example, the thermochemistry. For reaction, for example, reaction mean IRX input of reaction, CH2H. This is the name of the folders where the calculation of the molecules occur. So, for example, this Al, and then one CH3Cl plus OH minus, for example. This is the name of the folders, and then they take the output and then provide the enthalpy, entropy, and etc. in kilojoule per mole. We can also show the ER spectra and also the list of frequencies, mean IR, from the output of calculation, and then we can change NVChem with Orca and other software. We choose, there is no Gaussian or KeyChem or other commercial software. We only use open source or free software, or some software that we can get only by apply permission to one research group, for example. Yeah, we will add here. For example, one example. Wait a minute. Bhumita, you still can hear me?
Yeah, sure, Prof.
Okay.
Good.
So, for example, again, we can see here JMMDE pi y help, for example. We can, this is minus, wait a minute, minus S, where is minus S? Minus S is the name of the software we use. This probably and it is minus S software. Software can be Orca, DC, DFTB, GROMAX, and etc. Doc. And minus J is job. For example, single point calculation, optimization, frequency, molecular dynamics. This is metadynamics, TDDFT, doc, etc. Minus M is method, XTB, DFTB, B3, LYP, with its basis sets, for example, and etc. There is many facility to choose here. So the researchers don't have to worry about the syntax in each software. We can choose the software, and it will be developing. Okay, I think that's one example for CMDE post, for example, help. This all many. This is summary of the comment, and then double minus help is for help, job, method, input, and ERX is for reaction. 4 folders with the coefficient of the reaction, and this is for temperature. If we do molecular dynamics, for example. Oh, no, this is for output. Okay, and this is many options to process the data. Okay, I think that's all, Bhumita. Thank you for your attention to my talk.
Okay, thank you very much, Dr. Muhammad, for the great explanations about how to build the community to empower the research regarding computational chemistry. And the script that you have been developed is very interesting. It is convenient compared to other when we submit it manually to the software. And it is really helpful for chemists that never learned about programming before. And it is very convenient, and I hope it will be developed better and better. Okay. So we will start our discussion session. So I will invite again Professor Superhua as well as Bapak Dr. Muhammad Abdul Qadir Marto Prawiro for the discussions. For the participants that want to ask some questions or discuss some questions to get any advice and suggestions regarding your research, we invite you to don't be hesitate to write it down on our chat box. And here we have questions from YouTube, I guess, because we also live streamed our meeting in YouTube. So I would like to say hi also for all of you that follow us on our YouTube streaming. This is come from Ade Danova. Okay, thank you very much for your nice talk, Ajarn. It is for Prof. Supa.
Thank you.
Is it possible to investigate interactions between two different chiral inhibitors using computational chemistry? Because I have two compounds and only different one chiral centers, but both compounds show significantly different inhibitory activity.
Yeah.
So maybe we can start from Prof. Supa first.
Yes. About the chirality, we can calculate, and we have experience on that about the circular dichroism. Okay. And then we can model, for example, the natural products that have the different chirality, S and R configuration. And then we use the docking, also the binding of the enzyme that we would like to see the binding, and then we can screen, and then we can propose. Yeah. So it is possible to work on that. For experimental work, they cannot define which one is suitable for the appropriate bioactive compounds, but computational calculation can help. Yes. So I will give you this information first, and I will try to find the slides that probably I will show to you in a couple of minutes. So probably Professor Muhammad will have something to add or not?
Not now.
Okay. Yeah.
At least.
Yeah. So we can do it. Sure.
All right. Thank you very much for the answer. And I think we have another questions from Adani. She is our student. She wants to ask about QSAR. So what kind of errors that we will face when we use QSAR, and how do we overcome those errors? Oh, I think QSAR is a new a new material that our students have faced. So maybe Prof. Supa, if you want to further explain about QSAR, so please you can share again your slide, or we give you time for that.
Yeah. For the QSAR, it is the comparative. I mean the compare the structure in the same analog. Okay. So the different structure will provide the different activity. This is a concept. Okay. So when we have the errors, if you plot between the biological activity of the experimental and also the prediction, sometimes we found some outliers. Okay, outliers. We have to discuss, because sometimes the structure of the outliers quite much different from the analog that we train the equation. So we need to explain in the reason of the structure why it provide the outliers. Okay. So normally we need quite many of the analogs, the compounds in the analogs. If we have so many of them, then we can use some kind of the training set and the test set. And we can also perform the leave one out, okay, and try to reduce the outliers at the end. Then we can get a good model. So it's common to find the outliers. It depends on your data set. If you have many of them, then you can verify the good model and reduce the outliers. Okay. Limitation is that sometimes we have not much the compounds in the analog. So it produces quite outliers or errors, standard deviation of error of the errors. Yeah, that would be my answer.
Okay, thank you, Professor. And what if as you said before, how if the compound on analog is not that much? So how do we overcome? So do we search for another compounds on the another analog or something else?
As the concept of QSA, we need the same series of compound in the same analog. Okay. When we face the limited number, we cannot use other set of compound into the same set of compound because it comes from different laboratory, different testing. Okay, so that not appropriate ways. But I use another approach. For example, we can use docking. Yeah, the same target, and then we put the series of compound. Probably they come from different series or different laboratory, but we can see if those compound can put in the binding site. Okay, so we need other approach to work on if you have limited number of compounds. QSA is limited. That is the limitation of that is the limitation of QSA. Yeah, it depends on really the number of compounds.
Yeah, I would like to add, Bhumika.
Yes, yeah, that's good.
Yeah, sure, Prof.
Yeah, as Professor Supa said, QSAR has limitation because it needs many data to get good results. Yeah, Professor Supa. So, but QSAR is good if we don't know, haven't known, for example, the work of the drugs or the compounds, the interaction, etc. If we do know the interaction, we can do molecular docking, and also after that, using the method that I explained before, using DC, DFTB, we can do like rescoring using quantum mechanical methods. DC DFTB is good because in the past, quantum calculation is very, very slow, but using DC DFTB, it's much quicker, much faster. So because the result of the docking sometimes is not accurate, sometimes the sequence between among the compounds is not right, so we can do re-scoring using quantum mechanical method. That's some additional information.
Okay, thank you for the answer, Professor Supa and Pak Abdul Qadir. Thank you.
Okay, thank you very much for the answer, and also thank you, Adani, for the questions. Hopefully, next maybe you want to do some research in QSAR. So we are very welcome to facilitate you here because there is one student that has graduated from UPI, and she conduct research in QSAR under the supervision of Pak Hafiz here. And right, I guess we have other questions. yeah, how is data chemistry different with chemoinformatics? Maybe the questions could be answered by Bapak Muhammad Abdul Qadir Marto Prawiro first.
Okay. Actually, we don't know yet what is data chemistry because it will be a new field in chemistry based on methodology. But the data chemistry not only comprise of cheminformatics and also bioinformatics and also chemometrics and probably other tools to get insights about the rich data of compounds. For example, one family of compounds, alkaloids or etc. We can probably in the future data chemistry can have some insight if there is much more hydroxide or other groups in the natural product compounds. What's the trends of the properties, for example, in many properties, and so we can have some insights about the future of the family, not only the properties of the single compounds, but of the family of compounds. That's data chemistry in the future. That's one example.
Okay, thank you for the answer. Maybe Professor Supa have additional comments about that?
I think the new term have been rising. For example,
Okay.
cheminformatics. Cheminformatics is just, I think, very new area of research, just 20 years, and not much publications, but it is rising from now on. Actually, I have some slide, but probably I just talk. From now on, you will see it increasing. Yeah, so it new area of research, really very important one. Yeah, and so many things cheminformatics can be applied to research. One of the very important point, as Professor Muhammad mentioned, is that the database. If you have the database, then you can have some asset. Yeah. So many of the database right now, I think almost 100 million structures available of the chemicals around the world, many of the database. So it's nice to try to construct the database.
Yeah, one more thing, Professor Supa and Mita.
Yes.
In data chemistry, the new term data chemistry, it's also new approach to use machine learning to the data.
Yeah,
that's a new.
Yes.
Yeah, that's one more information.
Yes, and Professor Muhammad, if you think about QSA,
yep,
artificial intelligence, machine learning. Yeah, normally in terms of drug discovery, we use already machine learning for many years.
Yeah,
but the term machine learning just recently existing and very famous. Yeah, in the past we use, for example, self-organizing map, neural network, and so on, right?
Yep.
And right now, as you mentioned, machine learning is open the opportunities, especially in terms of catalysis. And then the scientists, many scientists around the world right now, they try to use ab initio to predict the structure, interactions, energy of the catalyst. And then they construct the database obtained from ab initio. And they try to screen the new catalyst. Okay, the same idea as virtual screening in drug design. Yeah, that means we need the database.
Yeah.
Natural product database, molecules, chemicals database. But on the other hand, the machine learning for catalyst, they have some kind of database of the catalyst. based on quantum mechanics calculation. Yeah.
And also our database, because if we try to find molecules, the research by Indonesian or Thailand researchers in Google Scholar, and then the summary of all research on some fields or some compounds, it will be difficult to find what's this the list of research from Thailand or Indonesia, for example. But if we have our country database, for example, so we can follow the development easily. Follow the development in our country. I think that's good. We don't have to worried about the redundant of data base, because the goal is different.
Yes. And Mita and Professor Muhammad, if you allow me to share slides.
Yeah, sure,
Okay,
Prof.
good.
For sure.
Just some slide that I would like to show. Okay. Where is it? Where is it? Where is it? Here. Okay. So as Professor Muhammad talked about the construction of computational science society in Indonesia, and I like to share a little bit about our community. We have also the Computational Science and Engineering Association, and we establish the symposium, the national symposium, every year. And this year is the 24th International Annual Symposium on Computational Science and Engineering. And then we will take turn the host from different university. So I think this is very good. And then probably in the very soon, we organize the next symposium. I will invite Professor Muhammad and also our colleague in Indonesia to share the experience together. Okay, I think this would be very good opportunities. This is the first point. And the second point, I would like to give you a little bit information about the database that we are constructed in Thailand, in Kasetsat. And you can see we are the same, sharing the same environment and diversification of natural resources, plant, animal, and microorganism, right? Especially in Indonesia, I have found that, oh, you have a lot of huge, I would like to say that 10 times diversity that compared to Thailand, we are very small. Okay, so, and digital provided opportunities. And here, these are the natural products database that we can do virtual screening. If you look, Germany, they have also 350,000 compounds. And these are the 3 databases from China. Okay, there are so many natural product database, and also this one from England and Austria. Okay, Brazil, and where else? This Brazil, and this is African. And for Thailand, we have chemistry base constructed from Kasetsat University, our department, from Thai medicinal plant, about 3,000, not much, but anyway, we try to do that. And the chemistry base, we have the 2D second version, and yeah, try to change from 2D structure to 3D structure and store it in the chemistry base with the molecular properties. And these are under the cheminformatics research unit from our department. I also engage with this. And if you look, we have the chemistry base, and we can use it virtual library, and we can do it screening of the compound. And just give you a little bit, there are some problem because due to the convert many of the 2D pictures to 2D coordinates, we have to clean data and to check the correction also and improve the data input in the input process. And here are the idea of information retrieve from 2D to 3D and then to store it as the coordinates. and also data process of the, we have to collect the plant name, okay, and clean data if there is a duplicate plants, and generate plant ID and add to the database and use the CAS, chemistry cast number, and duplicate, check again, cleaning the data and generate the 2D to 3D structure and put it using the RTF format, HTML format, or SQL format, and at the end, my SQL database constructed. So we now have two database, Chemi-based. Another one is TRI, which is the full name is the Thai Herbal Repository Access Initiatives. So I'm sure in Indonesia, you have also Indonesian herbal medicine, right? It's nice to put it in the database. And here are the computer technique for drug discovery from Thai traditional medicine. Yeah? And we use the TRI. And these are the language, very ancient language that explain about the Thai herbal medicine. Yeah. So now it's these materials are, very old. So we put it in the electronic format in order to conserve the information. Yeah. So it's nice, and pharmacopoeia and identification of active compounds, and also verification of drug activity. When we face the problem of COVID, we also look back to the Thai herbal medicine, yeah, and we found that Pha Thalai Chon, yeah, quite good for prevention, yeah, so it's quite helpful. These are the drug design and portal that we try to develop under development from time to time up to now. Yeah, and you can see the 2D to 3D and the process that we can screen 3,000 compounds in the database. And we try to practice for the HIV-1 reverse transcript test and protease, yeah, based on this database. And we end up for some candidate from our in-house database, yeah. So, and another one is very nice trial is that anti-neuraminidase screening when we face the problem of H5N1 many years ago, if you remember. So we screen the candidate from our own database and we obtain this candidate. Yeah, so it's nice, and we publish some work. And for our two database, they are connected. I mean, for Chemi-based, we got the structures, and for TRI, we got the Thai herbal medicine information, and then we can do some kind of computer-aided drug design. It's quite nice. And right now, we also interested in mushroom. If you have mushrooms, you can do also many mushroom. And I would like to say that mushroom is good. It is a source of proteins and many good bioactive ingredients, and also it is the food for future. Very easy to produce. And then we construct a number of mushroom actually in the whole world. It could be some kind of 140,000, but only 22,000 that are known, and approximately just only 7,000 that potential and benefit to humanity. Okay, but in Thailand we are very small. We have only 200, some kind of 250 species, and the mushroom that eatable just 75 species, and non-eatable mushroom 160, and poisonous mushroom about 8 that we have some information. So right now we just focus on 50 eatable mushroom and put it in the database, and we call it BACMUSH-based bioactive compound from mushroom database. Yeah, and here are ongoing, and we collect. You can see that this is the name in Thai, common names, scientific name, family name, and location that we found this eatable mushroom. Yeah, here are some kind of example Yeah, you know, linju. It is the mushroom that provide very good bioactive compounds, triterpenes and polysaccharides. So you can have the information and some physical chemical properties that we predict, yeah, and also 2D and 3D in the database. And here are the prediction of the admit prediction. Okay, so you can have so many properties from for example, the admit software that we can predict the properties. Yeah, so you can see that we can have you can construct this kind of database very easily, but you need the scientists to search information, to construct the 2D and 3D structures and optimize the structure, and then you can put it in the database. So we need the scientists. This is a new area of research that probably you can get the benefit from this kind of database. Yes, these are the example of the structure from linju only. Yeah, linju, you can have many of them, and you can put it in the database. And benefit of this kind of database can be provided to the bioeconomy and how to say, creative economy. Yeah, and the user can be researcher for drug discovery, entrepreneurs that they are working on the nutraceutical or cosmetics, and consumer for food supplements, even the smart farmers that they try to produce the high value mushrooms. So this is the way that I think opportunities open for the new and young generation to think about this. Not only natural products, mushroom, but also marine biodiversity that I'm sure in Indonesia you have a lot. And here are some kind of marine natural products distribution collection in 2002, and you can see sponge, red algae, brown algae, and so on. So many of them. Yeah. In China, they also collect. In Thailand, we have just small amount of marine species. Yeah. But all over the world, you can have many of millions of them. Yeah. It's nice. And here are the values that you can obtain from example of the marine natural products, bioactive compounds, and most of the FDA approved from natural products come from marine natural products as well. Yeah, so it's nice, antibacterial, antifungal, and so on. Yeah. So I think there are so many opportunities for natural products database in Indonesia as well. Yeah, just give you some information. Probably we can think about that, and we can work together. Yeah. And thank you very much. That is just the thing that I would like to share additional.
Thank you very much, Professor Supa. So yeah, it is a great insight for us. And I heard that Pak Kakak also has the same idea. Yeah, Pak.
One short comment.
Yeah, sure.
In 2016 or 17, one of theoretical physics from European Union said that it was difficult to find research happening in Indonesia compared with Thailand. That its Ministry of Research in Thailand has database of researchers in many fields. After that, Indonesian government accelerate the development and improvement of SINTA, our database as research of researchers. But we still lack many needs of other databases in the future. That's short comment.
Yeah, it's challenging to do that.
Yeah, challenging.
Just try to construct some more database first, and then you can expand.
Yeah. Okay, thank you for your sharing.
Yeah, thank you.
It is also a big work for researcher in Indonesia. We need some collaborations. We need to strengthen a lot of collaborations so we can build a kind of database.
Yep.
Yeah, and it will be very helpful for research development, especially in natural product chemistry and so on. We can also improve the food technology, drugs, and yeah, many things. All right, I think it is already 12 a.m. sharp.
Yeah, okay.
We have very interesting talks today. So before we end our meeting, I would like to invite again Professor Supa and Pak Kakak to give some closing remarks. Okay, from Professor Supa first.
Yes, and I would like to thank Department of Chemistry Education at UPI for kind invitation and provide me opportunities to give lecture series in computational chemistry. And I really happy to meet you all and sharing some of my experience. And I think that in the future, we should think about future. Yeah, I and Professor Mohammed are already senior, right? So we hope that the young chemists, young scientists, some researcher will do their best in the job, in the work, in the career, and we think about sustainable development. And to reach the sustainable development, we need basic research. Yeah. So this is the spirit of researchers.
Yep.
Yeah. Our future is that the scientists should think about responsible science. Yeah. I think this is the keyword that I very impression when the year 2019 that IUPAC celebrate the 100th year of IUPAC. And at the meeting there, they said, chemists, what shall we do? What we can do is that just do something that responsible science. Yeah, that would be a good statement that I would like to leave for everybody. Take home message. Thank you very much.
Thank you very much, Professor Supa, and from Dr. Muhammad.
Yeah, I agree and support the closing statements of Professor Supa. It's very good. So many challenges for new chemists, new born computational chemists in the future to use these the tools to benefit humankind. I think that's like also a responsible science and etc. And also we have to, in Indonesia, we have to strengthen collaboration, tear down the walls between institutions and etc. I think that's one of the messages for Indonesia. Okay, that's all. Thank you. And then also it is an honor to be invited to this discussion and then meet with Professor Supa.
Yeah, I was so very happy to see you.
Yeah, okay, nice to see you again. Okay, that's all.
Okay, thank you very much for both of speakers. On behalf of Department of Chemistry Education, we would like to say our gratitude for Hafiz, can you show? Okay, yeah. On behalf of the Department of Chemistry Education, we would like to say gratitude, and here is the certificate for Professor Supa Hanongbua, and also we have also for Dr. Muhammad Abdul Qadir Marto Prawiro, and we will send it directly to your email. This one. So thank you very much, and for all of the participants, you can fulfill the attendance link. And before we end our meeting, can we have photo sessions?
Yes, Sure.
photo sessions. Yeah, for all of the participants. Yeah, I hope you can open your video.
Well, my camera
Yeah.
is broken.
Unfortunately, yeah, but it's okay.
We have
Your
the
picture, your picture is so good. Okay.
Thank you.
All right, we have 2 layers in my computer here. So Pak Hafiz, can you help us to take the pictures? Okay, for the first layer, 1, 2, 3. Okay, and the second layer. Okay, 1, 2, 3. All right, thank you again for Professor Supa and Pak Kakak. Good luck for the CMMD in this afternoon, right?
Yeah.
Yeah.
Okay. Thank you.
And also Professor Supa, thank you again. Hopefully we can meet you again in another
sure.
occasion.
Yeah.
Yeah.
Thank you, everybody. Thank you, Mita. And
Yeah.
you
Thank you
all
very
are
much.
invited to visit me in Kasetsat, Thailand.
Yeah,
You
we
are
feel
all
honored
welcome,
to
Professor
have both
Muhammad.
of you.
Okay. Thank you.
ขอบคุณค่ะ Take care, everybody. สวัสดีค่ะ
Okay. See you.
See you.
See
Bye
For
bye.
all of you,
Hope you
Professor
always can
Supa,
get
Mita.
along.
Thank you so much.
Yeah,
ขอบคุณ
thank you
ค่ะ
very much.
Thank you, Hafiz.
Thank you. Okay. See you.